Hello everyone, welcome to the fourth lecture of QM101. This is another mathematical interlude. So here we will continue our discussion which we started in the previous lecture. So recall that in the last lecture we studied we learned what is an inner product, and that is it's a function which takes two vectors as an input from the vector space and gives outer number. That number as in it's an element of some certain field, which in case of quantum mechanics is almost always the set of complex numbers. Now given a vector space V, there exists another vector space called V star, which is set of all the functions, all the linear functions which take vector as an input and gives a number as an output. So such a set of all such linear maps is called V star, or the dual space of V. In short, dual of V. We usually denote it with V star. Now this map V star, it has a one-to-one correspondence with the set V. That is, there for every element in V there exists an element in V star, and that map is not really canonical in the sense there is no direct correspondence, like given a vector space you can just find a V unless you have a inner product defined on it. So once you define an inner product on the vector space V, you can find a corresponding element in V star. So just it is not canonical in the sense that the choice of element in V star, so suppose it's V, then the corresponding V star which is in V, this V star corresponding to this V depends on the choice of inner product. So if you have one inner product this, and then another inner product this, then both of these will give you different V star. Okay, so in that sense this choice is not canonical, but there is one-to-one correspondence. Now now suppose you are defined an inner product, and then you want to find what is the corresponding element in V star. So that element is given by this map psi V. In previous video I just used psi, I think this here I am using psi V to denote that is some map with on set V. So given a vector V, it maps it to a function phi of V, such that here it takes input. If the input is some vector, here you can, in the place of dot you can put any vector. And how is it this function defined is that for in the inner product you just put the element V in the first entry. So V is all, you define the first element, and now second element you can put whatever you want. And since second element needs to be a vector from the V, the vector space V, so here you put some U which belongs to V, then it will give you a number. So apparently, so technically this thing here you gives a vector U from V and you get a number as an output. That's why in that sense it is a linear functional, and it is linear because as we said that the inner product is linear in the second argument. Okay, so in this way you can define a map in V star corresponding to this element V. Now this is typical mathematical notation. If you want to write in bracket notation, which we are using so far and which we will use in future for quantum mechanics, so it simply means that you're taking a ket vector and you are sending it to its corresponding bra vector. So this is a ket and it is corresponding bra, and they are called dual. This kind of vector is called dual vector. So this thing, it is dual vector of V. So bra is dual of ket and ket is dual of bra, and so on. Okay, so there is this relationship that we call it a dual vector. Now that we have the correspondence between V and V star, and as I said that these are like these two vector space although they are different vector space, one is a set of vectors and then there is set of functions, they are essentially the same in the sense they have the same vector space structure. They have, for every v there is a corresponding v star or dual of v, and it has the same properties like linearity and so on. So that's why this is the algebraic structure of these vector spaces is the same. That's why a lot of people, when talking about these vector spaces v and v star, they basically treat them as the same vector space, but remember that mathematically they are not the same vector space. Okay, now that we have the concept of dual vector, we move on to the next concept, which is the adjoint operator. Now adjoint operator is a operator on the dual space. So suppose you have a map from v to v such that it takes a vector v and gives you some another vector v prime, or you can also write it as ket of dv. Okay, like some people write like this, some people write like this, so it doesn't really matter. Now since one vector is sent to another vector via this map, there is a corresponding map which sends the dual of this first vector to the dual of second vector. So there exists a map such that this t dagger, which takes the dual of this vector v, which is the bra of v, and gives you the dual of this vector v prime or bra tv. Okay, and this thing t dagger taking v, bra v as input, the usual notation for this is to write the bra vector first and the t dagger later. So we basically write it like this. This is how we write it. Okay. So this t is dagger is called the adjoint of t. Now that we have the adjoint, there is a concept called self-adjoint. So a self-adjoint operator is an operator which is all such operators where t dagger is basically equals to t. But what does this mean? Because t is a vector from v to v and t dagger is a vector on v star to v star, so basically they are maps on different sets itself. So how can they be together? Because for two maps to be same, they have to be they need to have the same domain and codomain. So these are equal in a different sense. They are equal in the sense, so this is correct but not exactly correct. I'll come to this what is the correct notation. So a dual vector is a vector where, now suppose you take self-adjoint map is a map where if you take any two vectors u v from the vector space, and if u t dagger v is same as u t v, then t dagger is called self-adjoint. This same thing can also be written as u tv is same as tu v. So any any map or operator which satisfies this property is called a self-adjoint operator. Now when you write the matrix of this corresponding to this operator. So as you know, all the linear maps can be written as a matrix. So when you write a matrix for this operator, and I'm denoting the matrix corresponding to the t operator as square bracket of t, then so suppose this is the matrix corresponding to the t vector, and this is the matrix corresponding to the t dagger vector. So now this is a result I'm just directly stating, is that the matrix corresponding to t dagger is the Hermitian conjugate of the matrix corresponding to t, and this dagger notation is also used for representing the Hermitian conjugate. What is a Hermitian conjugate? So it is basically you transpose the matrix, that is you convert rows into columns and columns into rows, and you take the complex conjugate of every element. So suppose the element of this T matrix are Tij, then the T dagger of Ij is basically the Ij element of this T dagger matrix is basically Tji complex conjugate. This is what we mean by Hermitian conjugate. So you transpose the matrix of T and take a complex conjugate, that is the matrix corresponding to T dagger. So this is an important thing, and here in this sense, so this relationship holds for the matrix. So when you write the matrix corresponding to T and T dagger, you will notice that the matrix of T dagger is same as matrix of T. And this is what it means. So it's not that these maps are equal, it's just that their corresponding matrix representation is the same. Okay, that's what we mean by. And this matrix representation is such matrices which have these properties. These are called Hermitian matrices. So the self-adjoint operators are represented by Hermitian matrices. That's why they are also called Hermitian operators. Now Hermitian operators, as I said, are very useful because I must have mentioned it in the video where I explained the postulates of quantum mechanics, is that all the observables, basically things like energy, momentum, position, etc., etc., they are represented by Hermitian observables in quantum mechanics. Okay. Now why do a Hermitian operator correspond to a observable? It does so because of the following theorem. So now there is theorem, and I'll not prove this theorem because it's really easy to prove. You can find it in any book. The theorem is that all eigenvalues of an Hermitian operator are real. So if T is a Hermitian operator, that is T dagger is same as T in the matrix notation, then and lambda, get lambda is some eigenvectors corresponding to this T, which is the eigenvalue lambda, then lambda is a real number. It's not a complex number in general, because the vector is defined on a field of complex number. Any operator can have a complex eigenvalue, but the Hermitian operators has the property that has to be a real eigenvalue. And since eigenvalues corresponding to the values that one can observe in a system, that's why you cannot, when you say observable have to be Hermitian, is that they need to have real eigenvalues, because eigenvalue corresponding to the value which you can observe, which you can measure, and you cannot have a complex value for something which you can measure. Okay, you cannot write a complex value of momentum or complex value of energy. those values has to be real. That's why the hermitian operators defines the observable, because corresponding eigenvalues are real and eigenvalues are something that we can measure in an experiment. Now along with this, there are other theorem, also important theorem about hermitian matrices as well, is that if T is hermitian and have following eigenvalues, that is T is a hermitian matrix, and if you find the eigenvalues to be lambda 1, lambda 2, lambda n, and the corresponding eigenvectors ket lambda 1, ket lambda 2, ket lambda n, then the following thing holds, that if lambda 1 is not, sorry, if lambda I is not equal to lambda j, then lambda I, the inner product of lambda I and lambda j corresponding the vector corresponding to lambda I and lambda j is delta ij. That is, they are orthogonal to each other. So all these vectors, the eigenvectors, they are orthogonal. Orthogonal is basically generalization of perpendicular. Sorry, not delta ij, it should be 0 if they are not the same. And if they are the same, if there are two eigenvalues which are the same, then you can, it does not imply that this has to be 0, but you can choose it to be 0. So basically, if there are two, suppose lambda 1 and lambda 2, they are the same, so the corresponding eigenspace, that eigenspace is basically a subspace of the vector space, there you will have, this will have some v1 and this will have some, so then you can have to find two vectors correspond to represent this entire eigenspace, because with a single vector you can just get this one dimension of this dimensional space. You need the entire plane. So for that you will need to choose two vectors, lambda 1 and lambda 2, and you can choose these vectors orthogonally. Basically you can choose that these two corresponding vectors are different. Yes. Also it might also, okay, so this is the thing, if the two eigenvalues are different, they are definitely orthogonal. If two eigenvalues are the same, that is, you are not, and it's not that you are counting the same eigenvalue twice, it's that there are two eigenvalues which are same, then in that case you can choose two eigenvectors to be orthogonal to each other. Okay, and the last is the completeness theorem. So completeness theorem says that any vector which hermitian operator gives can be written as a linear combination of its eigenvectors. So suppose there is a Hermitian map T from V to V, and you apply this map T on some vector V and gives you some vector V prime. Now this theorem says that this V prime can be written as some linear combination of Ci of all the eigenvectors lambda I. Now this completeness theorem can be summarized in a single expression, and that is the identity operator on V can be written as this. This is a one-line expression for the completeness theorem. Now how does this correspond to this? It's really simple to see, is that V prime is identity of V prime. Identity is basically this, it doesn't change anything, and instead of this identity we can insert this thing, lambda I V prime. Now this bra here, it acted on V prime and gives you basically this becomes an inner product, so it will give you a number, and we call this number Ci, and since it's a number it can be taken here this side Ci, and this is lambda I. So all such vectors which this map T generates can be written as a linear combination of the eigenvectors, and the corresponding coefficient Ci is basically lambda I cross V. Basically the projection of this vector V on the eigenvector lambda I gives you that vector. So this is the completeness theorem. So generally in books, when you see completeness theorem, you will often see this expression and a corresponding expression for a continuous spectra. So suppose there, instead of like n finite eigenvalues, there are like infinite number of eigenvalues which are varying continuously, which often happens in quantum mechanics and sometimes which often happen in quantum field theory and sometimes in quantum mechanics as well. So it is written as like this, same thing but in for continuous spectra instead of discrete spectra. So to summarize, in this video we learned about what are adjoint operator, what are the self-adjoint operator, and the very important properties of these self-adjoint operators or the Hermitian operators. That is, the eigenvalues are real, the eigenvectors are all orthogonal, and make them orthonormal by Gram-Smith procedure, and the completeness relation, that is any vector, output vector of those Hermitian vectors can be written as a linear combination of the eigenvectors. And with this we conclude this lecture. So in the next lecture we will hopefully start with some physics, or maybe I will need a little more mathematics. Let's see, let me plan my next lecture and then I will tell you. Till then, see ya. Also, if you like the video, then like the video. If you like the video, then click the like button and subscribe the channel, and see you in the next video.